Hello, my name is Greg Belgrad, and this video is designed to be a tutorial to help solve problems given on the last test that people might have had a little trouble with. So this problem specifically is problem 4, and it entails a mountain climber on the side of a cliff attached to a rope of unknown tension, and that mountain climber is exerting a force of unknown magnitude, and our job is to try to find the tension and the force given the mass of the mountain climber and the angles at which those forces occur. So the first question is to find the tension in the rope required to keep the mountain climber stationary. So the first objective we have to do is to find all the forces acting upon the system. Well, the first force to tackle will be the tension force. You have to break this up into its y and x components. The y component is equal to the magnitude of the tension force times the cosine of 31 degrees, which is the angle, and the x component is that tension times the sine of the angle, which is 31 degrees. And then you also have the force of the mountain climber acting directly upon the cliff. And you have to break that up into its components again, the x component being the magnitude of the force times the cosine of the angle, which is 15 degrees in this case, and then the y component, which is the magnitude of the force times the sine of 15 degrees. So then the second component is to create a system of equations. Well, the mountain climber isn't moving horizontally. In fact, it's not moving at all. So in the x direction, given that the tension force and the force of the mountain climber acting in opposite directions, you can write an equation saying that the magnitude of the tension in the x direction minus the force in the x direction is equal to 0. But in the y direction, there is a downward force equal to the mass of the mountain climber times gravity. So you have to equate that, if it's not going to move, to its y components for the other forces acting on the system. In this case, you have the y component of the tension, which is t times the cosine of 31 degrees, plus the magnitude of the force times the sine of 15 degrees. So then you have to solve and substitute those values in. So the easiest equation to solve would be the x equation, and you can equate t times the sine of 31 degrees to the magnitude of the force times the cosine of 15 degrees, and you have to solve for f because we're going to find the tension. So you can solve for f, which is equal to the magnitude of the tension force times the sine of 31 degrees divided by the cosine of 15 degrees. And you can substitute that value into the y equation. And then you have a new y equation, which is equal to t times the cosine of 31 degrees plus t times the sine of 31 degrees divided by the cosine of 15 degrees times the sine of 15 degrees. Because in the initial equation, we had that f times sine 15 degrees. But since t times sine of 31 degrees over the cosine of 15 degrees is equal to f, you do have to multiply that whole value times the sine of 15 degrees, and you equate that to mg. So then, mg equals t times cosine of 31 degrees plus t times the sine of 31 degrees times the tangent of 15 degrees, and it's just simplifying it, given that the sine of 15 degrees in this over here over the cosine of 15 degrees here can just simplify the tangent. And then you could simplify it even more by grouping the values. So you could take out the t here because they're both multiplied by values, and then you could put it into parentheses, and then you could, even further simplifying it, making the magnitude of t equal to mg divided by cosine of 31 plus the sine of 31 degrees times that tangent of 15 degrees. So then over here we have 60 kilograms times 9.81 meters per second squared over that bottom value, which turns out to be 0.995, and then you have your magnitude of the tension force equal to 591.46 newtons. So then the second part of this equation requires us to find the force of the mountain climber acting upon the wall, acting upon the cliff. And we have to find the value of the force required for the mountain climber to remain stationary. So the first part is, again, find the forces acting upon the system, which is the same for the previous question, and then you have to create the same system of equations, and then you solve and substitute, but this time we're solving for f. So again, you can start with the x. You can start with the x component, equate the values, and then solve for t. And the magnitude of the tension is equal to the magnitude of the force times cosine of 15 degrees divided by the sine of 31 degrees, and you can substitute this t into the y. So then your new equation for the y is equal to the magnitude of the force times the cosine of 15 degrees over the sine of 31 degrees times the cosine of 31 degrees plus f, the magnitude of the force times the sine of 15 degrees, equals mass times gravity. So then again, you could group your values. The magnitude of f is equal to the cosine of 15 degrees divided by the tangent of 31 degrees, and that just and you can find the tangent by dividing the cosine of 31 degrees, dividing by the sine of 31 degrees, and that's equal to cotangent, but cotangent is equal to 1 over tangent, so then you can just, again, simplify it even more. So that's how you derive that. And then you add 15 degrees on the bottom and you get your mg, and then you can solve for magnitude of force by taking mg and dividing it by that whole term, and these are the resulting numbers. So 60 kilograms times 9.81 meters per second squared divided by 1.866, which is what this term is, and then simply you can just multiply and divide, and then you get the magnitude of the force being equal to 315.37 newtons. So then the last question is calculate the minimum static coefficient of friction between the climber's shoes and the cliff required to remain motionless. So you have to write down the force of friction equation, and the force of friction is denoted by Fr equals the coefficient of static friction, which is the coefficient of friction required to start moving an object. So this is the coefficient of friction of a motion of an object at rest times the normal force. So then you have to find its components. So in the x direction, the friction force has to be equal to the magnitude of the force of the climber acting upon the cliff, which is equal to the magnitude of F times the sine of 15 degrees. And for that to remain motionless, these quantities have to remain equal. And then you have your y component, which is equal to the normal force, which is equal to the magnitude of the magnitude of the force vector times the cosine of 15 degrees. And then you can substitute and solve. So if the F friction force is equal to the magnitude of F times the sine of 15 degrees, you can substitute that in, and then you can find the normal force, which is equal to F times the cosine of 15 degrees, which is equal, and then you could take, you algebraically solve for mu s. You could stack those values. You can divide F sine 15 degrees divided by F cosine of 15 degrees. Those F's cancel, and then the coefficient of static friction is just equal to the tangent of 15 degrees, which is then equal just to 0.268. And that's pretty much how you solve the whole problem. Hope this helps.